Welcome to the another class of design of RCC structure. This is the continuing lecture of design of column. So in this lecture you will going to learn axially loaded short column with helical reinforcement. Now you can see the figure, helical reinforcement needed where the column is circular, and for circular column we need minimum 6 number of main longitudinal bar, okay, and the tie bars are spiral here. If you see longitudinal section, you can see the tie bar are spiral here, okay. That's why this is called helical reinforcement, okay. So that means this kind of arrangement actually called helical reinforcement. Before we read it out, let's check the IS code consideration. For helical reinforcement, IS code consideration is given in clause number 39.4 of IS 456 2000. Let's check it out. As per clause number 39.4, as you can see here, compression member with helical reinforcement. The strength of compression members with helical reinforcement satisfying the requirement of clause number 39.4.1 shall be taken as 1.05 times the strength of similar member with lateral ties. So that means for helical reinforcement we have to multiply 1.05 with this formula. Pu is equals to 0.4 FCK AC plus 0.67 Fy ASC. So we have to multiply 1.05 with this, okay. Now as per clause number 39.4.1, the ratio of the volume of helical reinforcement to the volume of the core shall not be less than 0.36 into Ag by Ac minus 1 into FCK by Fy. Now, where Ag is gross area of the section and AC sometimes in somewhere it may be taken as AK, AC or AK is area of the core of helical reinforced column measured to the outside diameter of the helix. FCK is characteristic compressive strength of the concrete and Fy is characteristic strength of the helical reinforcement, but remember not exceeding 450 Newton per millimeter square, okay. So let's check the notes. So the strength of a column with helical reinforcement is calculated as following as per the clause number 39.4. Pu is equals to 1.05 into 0.4 FCK AC plus 0.67 Fy AC, as I said earlier. Now columns with helical reinforcement or spiral are more ductile and have improved strength. Thus, their load carrying capacity is more than that of the columns with lateral ties, okay. As per IS 456 2000, the safe load of for columns with helical reinforcement is 1.05 times the safe load carried by a similar column with lateral ties, provided the requirements given below are fulfilled, okay, which we read out in code also. The ratio of the volume of helical reinforcement to the volume of the core shall not be less than 0.36 into Ag by Ak minus 1 into Fck by Fy. In right side you can see the diagram This is a cross-sectional diagram of a circular column or a column with helical reinforcement. You can see the core diameter here, and main bar and spiral bars are also denoted. Core diameter is denoted by d suffix c, and hole diameter is denoted by capital D. Okay. Now, as per the consideration which is written in clause number 39.4.1, volume of helical reinforcement by volume of core should be greater than 0.36 into Ag by Ak minus 1 into Fck by Fy. Now, Ag is cross-sectional area of column, so it will be pi by 4 into capital G square, that means whole diameter square for a circular column. Ak or Ac, whatever you want, you can write. Area of the core of helically reinforced column measured to the outside diameter of helix. Okay. So, it measured to the outside diameter. Okay. Fck is characteristic compressive strength of concrete. Fy is characteristic strength of helical reinforcement, but not exceeding 450 Newton per millimeter square, as we read earlier. Phi is diameter of spiral, and small p is pitch of spiral. Okay, pitch means the center to center distance. Okay. Now, Ag is equals to pi, so that's why Ag is equals to pi by 4 d square. Ak is equals to pi by 4 dc square. Now, dc diameter of core, whole diameter minus 2 into end cover. Okay, because there are in two sides there are there is cover. D dashed means the inner core diameter, that is equals to d minus 2 into end cover minus phi s, that means diameter of spiral. This is how we can find out the inner diameter of the core. So, outer diameter of the core is dc and inner diameter of the core is d dashed. Volume of helical reinforcement per mm height of column is equals to circumference of spiral into area of spiral by pitch of spiral. So, that is equals to pi into d dashed into pi by 4 into phi square by p. Okay. Circumference of spiral is pi into d dashed, and area of spiral is pi by 4 into phi square. Okay. And pitch is p. Volume of core per mm height of column is pi by 4 into dc square into 1. And steps are for designing is same as lateral dies, which we cover in previous lecture. So, let us solve a problem that will help you to understand better these assumptions. Okay. So, this is the problem in your screen. Design a circular column of diameter 400 mm subjected to a load of 1200 kilonewton. The column is having spiral ties. The column is 3 meter long and is effectively held in position at both ends, but not restrained against rotation. Use M25 concrete and Fe415 steel. So, this is the problem of helical reinforcement. We have to design a circular column with helical reinforcement. End conditions are given here. Okay. So, what is given in question? The length of column capital L, that is 3 meter. Axial load P, capital P is 1200 kilonewton. Diameter capital D is 400 mm, Fck is 25 Newton per millimeter square for M25 concrete, and Fy is 415 Newton per millimeter square for Fe415 steel. So, first of all, we have to find out effective length. So, LEF, effective length for the condition column is effectively held in position at both ends but not restrained against rotation. Let's check it out. Table number 28 of IS 456 2000. Now in table number 28 of IS 456 2000 we have to find out our end condition. So you can see in extreme left column, number 3 is our end condition as per the problem, effectively held in position at both ends but not restrained against rotation. Look, symbol is also given. Okay. So recommended value of effective length is 1L. So we should take this. So effective length is 1L, then so slenderness ratio is equals to L by D, that is equals to L, here L effective and L is same. So 3000 by 400, that is equals to 7.5, and this is less than 12. So as per IS code specification, this column will be designed as short column. Now minimum eccentricity, E minimum is equals to L by 500 plus D by 30, that is equals to 3000 by 500 plus 400 by 30. This formula is written as per clause number 25.4, that is equals to 19.33 mm, which is this is a printing mistake, which is less than 20 mm and which should be less than 20 mm. Okay. This will be 19.33 is less than 20 mm. So we can assume that E minimum is 20 mm. So E minimum by D is 20 by 400 is equal to 0.05. So it is limited to 0. E minimum by D is limited to 0.05. So it is designed as axially loaded column as per consideration, IS code specification. Now area of steel. Now first step is PU. To find out PU, you have to multiply partial safety factor 1.5 into axial load, that is P. 1.5 into 1200 is equals to 1800 kilonewton or 1800 into 10 cube Newton. Now for a column with helical ties, the load carrying capacity is given by PU is equals to 1.05 into 0.4 FCK AC plus 0.67 FY AS as per clause number 39.4. Here AG, gross area, is equals to pi by 4 into 400 square. So this is the value of this AG. Now AC is equals to AG minus ASC, where value of AG is known. We can put this value like this. Okay. So from this we can find out the value of ASC. After calculating, the value of ASC is 1793 mm square. Okay. So percentage of steel will be as per this equation, right? Will be as per this equation. So that is equals to 1.43%, and this is in between 0.8 and 4%. Hence it is okay, right? Now using 20 mm dia bars, if you use 20 mm dia bars, that means diameter of one bar will be 314 mm square. So number of bars required 1793 by 314 is equals to 4.7. But as I said earlier, for circular column we need minimum 6 number of bars. So we will provide 6 number of bars. So provide 6 number of 20 mm dia bars. So area of steel provided 6 into 314, that is equals to 1884 mm square. Now the calculation for helical reinforcement. Now the core diameter we have to calculate. If we assume clear cover is 50 mm, then core diameter DC is equals to hole diameter 400 minus 2 into end covers 50 mm, that is equals to 300 mm, and area of core pi by 4 into 300 square minus 1884, which is area of steel. So, that is equals to 6880.8 mm. This is the area of inner core. Okay. Now, assuming pitch, volume of core per pitch is area of core into P, that is 6880.8 into P. So, using 8 mm spiral dia, that means if we use 8 mm spiral dia, we provide here, volume of one spiral per pitch is pi by 4 into 8 square into pi within bracket 300 minus 8, that is equals to 46,110.8 mm square. Now, we have to put this in this consideration formula, the volume of helical reinforcement by volume of core. So, volume of helical reinforcement is 46,110.8 by volume of core, which we find out earlier. This is the volume of core. Volume of core is 68,801.8 P. Okay. So, as per IS code, this volume of helical reinforcement by volume of core should be less or equals to 0.36 into Ag by Ac minus 1 within bracket Fck by Fy. So, you have to calculate this one. So, from this equation you can find out the pitch. So, here pitch is, small p is greater or equal to 37 mm as per the consideration. Now, the minimum pitch should not be more than 75 mm or core diameter by 6, that is 50 mm. So, it should not be more than 50 mm maximum pitch, and minimum pitch is 25 mm or 3 into diameter of helical reinforcement, that is 3 into 8 is 24 mm. So, it should be between 24 mm and 50 mm. So, we can take it as 40 mm, therefore, provide 8 mm dia spirals at 40 mm center to center as shown in figure. Now, look the figure. At upper portion, the cross section of the circular column, outer diameter is 400 mm, 6 numbers of 20 mm main bars is provided, 8 mm dia spiral bars at 40 mm center to center is given, and this is the longitudinal section to better understand the spiral reinforcement arrangement. Spiral reinforcement arrangement is like this, and pitch distance, the 40 mm, is calculated like this. Okay. So, here the design of short column, axially loaded short column with helical reinforcement is complete. That's all for this lecture. Thank you.